Thank you. Thank you for the introduction and thanks for the invitation to speak here. I'm very happy to be at this conference. So, as Milena said, I'm going to tell you about real tropical quartics and their bitangents. And we're going to use patchworking to count them. A little bit of the story was already told by Angie on Monday, and she also already gave a very great introduction to the topic. However, this was Monday, it's Thursday. I assume we heard a lot of different topics in between, so I'm going to go over the introduction again, and hopefully you recognize things from Monday and feel happy about this. Yes, so this talk is based on a paper that's joint work with Marta Panizut and new preprint that's just on the archive this week. Okay, so start with again, what is tropical geometry? So we heard two slogans from Angie on Monday. The first was tropical geometry is algebraic geometry over the tropical semifields with real numbers with negative infinity. In algebraic geometry, we work with zero sets of polynomials or algebraic curves in our case here. And when we tropicalize, we get something like this. So this is a tropical curve. It's a polyhedral complex. And in this sense, tropical varieties are combinatorial shadows of algebraic varieties over boundary fields. So this is kind of the picture that you should have in the back of your mind to these two slogans from Monday. So in terms, I have a few definitions in the set, so remember this picture. And now we go back into what we've seen on Monday. So classically, we have our field K with evaluation. You can think of the Bézier series that we've seen a couple of times. C with the t-adic valuation, where I remember the valuation remembers the lowest coefficient of exponent of t, or over R, the same thing, or the p-adic number field with the p-adic valuation. And tropically, we have the tropical semifield with the tropical addition and tropical multiplication, which are taking the maximum, and that's the addition tropically. And the tropical multiplication is just our classical addition over the real numbers. Now, if we have a classical polynomial and tropicalize it, there are two things that we have to do. The first thing is we need to substitute the operations of a k to the tropical operations. So taking the sum becomes taking the maximum, and all products become sums. And then we need to take care that we're over the correct field. So from K, we move into the tropical semifield by taking the negative valuation. So our sum here of a gamma x to the power of gamma becomes the maximum over the negative valuation of a gamma plus gamma times x. If we're now looking at our actual algebraic curve or hypersurface, I have the variety of this one polynomial, so the zero set. And there are two things that I can do, and it's a theorem that Angie already presented on Monday, that these two ways to look at this are the same. So the first is I can look at the points that satisfy f of y equals 0, and I tropicalize them by taking the valuation, so minus val, and then I need to close this up under the Euclidean topology. This is one way to tropicalize the variety. The other is to say, okay, I'm going to look, instead of at the points, I'm going to look at the condition f of y equals 0 and tropicalize that. And this amounts to looking at those points where the maximum in trop of b is attaining these twice. And both of these give you the same set. That's the plan. So far, so good. So I'm going to tell you about Quartic curves, and we're going to see a lot of Newton subdivisions. So we need this concept of duality that we've also already seen in a couple of talks, in Amy's talks, but also in Sabrina's talks. There were pictures of polytopes with subdivisions. So I'm going to explain this very briefly. We have our polynomial f, and we take the Newton polytope as the convex hull of those points gamma, where gamma is the exponent of x, and a gamma, the coefficient, is non-zero. Let's look at these things with an example. So here is our polynomial f over the Bézier series. So my exponents are these t to the power of something. There could be sums in t to the power of something, but this is a very easy example. So just t to the power of minus 3 minus 2 as exponents. And then I have the tropical polynomial here. Okay, so just remember what we do when we tropicalize this polynomial. We take the negative valuation of the exponents of the coefficients. So 1 becomes 0. The next term is t to the power of minus 3 times x. So t to the power of minus 3 becomes 3, negative valuation. And then the product becomes the addition, so plus x. Okay? And then x squared becomes 2x, and so on. And then I can do, as we have seen on the previous slide, I can look at, well, where is the maximum achieved at least twice, or I can look at the actual points in the algebraic variety, take their valuations, and close this up, and then we'll get this picture. This is our tropical curve corresponding. One way you can see this, you can just like, as in one example, we can plug in like, let's take this one, minus 3, comma minus 2. If we plug this into the tropical polynomial, what do we get? We get the maximum of 0. 3 plus minus 3 is 0. 2 times x, that's minus 6. 2 plus y is minus 2, 2. So 0, 3, and so on. Like, okay, so I don't have to do the math for the last 2 minutes, okay? But you believe me, so when we see the maximum will be the 0, and it will be achieved 3 times. In this. And so this tells you this vertex lives on the top. Okay, so now to the duality. So let's write down the new polynomial for this polynomial. Okay, so I put in a lattice point for each of the exponent vectors. So I have 0, 0. For x, I get 1, 0. For x squared, I get 2, 0. Xy gives me 1, 1. And so take the convex hull. This is my new polynomial. And now to get the subdivision, this new subdivision that we need, we're going to remember the valuation that corresponds to the tropical coefficient, let's say, that correspond to those monomials. So I'm going to do this. So for the constant one, I have a 0. For x, the coefficient is 3. 2x, the coefficient is 0, and so on. And now I think of these as a third coordinate. And you had a very nice 3-dimensional picture on the blackboard on Monday. Even though these are slides, I only have a 2-dimensional picture for you. So what you have to think of, there is a third axis that's coming out of the wall here, right, towards you. And these numbers here tell you how far the points come out of the wall. So there's those with 0, they just stay on the wall. However, this one, 1, 0 with a 3, that comes out 3 steps out of the wall is there. Okay, and the others as well. And then you take the convex hull and look at the upper faces. So what you will see is some kind of roof, okay? And it will look like this. And this is the subdivision of the new polytope. And this is dual to this curve by the following way. Each triangle here corresponds to a vertex here. And each edge here, so for a facet, these are the edges of the facets, right? I take the outer orthogonal normal vector, and that gives me the direction of the edges that correspond to these, to the vertex. So I have my vertex here, my triangle here corresponding to the vertex here. Let's keep it straight, okay? And then this vertex is adjacent to 3 edges, which correspond to the 3 facets over here. Right? So this facet corresponds to this edge, outer normal vectors. So this is, by looking at this picture, just these numbers and the subdivision, we have all the information about this tropical curve. I wouldn't need to draw this picture anymore. All the information is stored. Questions? Good. Now we can get to tropical quartic curves and their tangents.
So on the left, how would you know the vertices of the right, for example?
So here, okay, so this, I can compute this vertex by saying, I know that these 3 linear, each vertex here corresponds to a linear term in this polynomial. And these 3 vertices tell me that these linear forms take the maximum, are equal and take the same maximum within all of these linear forms at that vertex. So I would say, okay, I need to compute 0 equals 3 plus x equals 2y. And this has to be bigger than all the other terms. And well, the solution of this is minus 3. So this is how you can compute. That's the question. Okay, tropical bitangents. Before I go to this, sorry. Before we go there, I want to tell you the actual question behind this, behind the story. So we've seen how we get from algebraic varieties to tropical varieties by tropical. Now we can ask ourselves, if I have my tropical variety, I want to get back to an algebraic variety. This is what we call a lift. So if we have a tropical variety, we lift the tropical variety to an algebraic variety. That in turn, if we tropicalize, we get back to T. So far, so good. If you remember the first this polynomial I had as an example with a duality, you might think, oh, well, there will be infinitely many. Like in the example on the previous slide, I could have chosen my coefficients to have any higher order terms additionally to the like t to the -3. I could add any element in the series with higher order, and I would get the same tropicalization. So there would be infinitely many algebraic ones. This is what Angie said on Monday, tropicalization is highly non-objective. A lot of things tropicalize. So maybe we can make the question more interesting or more concrete if we say, hey, what if I have two tropical varieties that are in a certain relation to each other? So maybe they're contained in each other, or in our example, they're bitangent or tangent. So two tropical varieties having a certain relation to each other. I fix a lift of the first one. I have my V1. And now I'm asking, can I find an algebraic variety that is a lift of the second, T2, that satisfies the same relation to on the same algebraic relation on the set of like on this variety. So classical examples would be I have a tropical cubic surface. I lift it to an algebraic cubic surface. I have a tropical line that lives on my tropical cubic surface. I have my algebraic surface up here that contains 27 lines, and the question is like, is one of them the lift to the tropical? And what we're going to look at is we will have a tropical Quartic curve and a fixed lift, the Quartic curve, and we will have our bitangents here, and we will look at bitangents. So this is the story. And if there exists such V2, and we can count how many there are, and this is called the lifting multiplicity. This is also a word or like a term that you hopefully remember from Monday. All right, so as I said, like in our example, you have a tropical Quartic curve, so that's the black one here on this side, and our classical Quartic curve, so that's the blue one on this side. And this one has 28 real bitangents. These are the red lines. And tropically, there are 7 classes of bitangents. What this exactly means, we'll see later. There are these decorations on the graph. We'll see how they correspond to each other. So first, before we do this, we need to understand what I mean when I talk about bitangents of tropical curves. So here in black we have our Quartic curve, and in red we have our tropical line. So this intersects in 2 places, and these are obviously very different. Right? So here I get a unique intersection point, and here I get a whole line segment. We need to understand how we compute the intersection multiplicity. So for a transversal intersection that we have here, we have just one intersection point, right? The intersection multiplicity is determined by taking the weighted direction vectors of the edges that intersect, and we take the absolute value of the determinant. So this weighted, you don't need to worry about it, because in our case the weight is always 1. So we only need the actual direction vectors of the edges, the primitive. So in our example, we have these 2 directions, and so one is -1, 0, the other is 1, -2. I take the determinant, the absolute value is 2. So this is a tangent, right? So what about the other case? So in the other case, I don't have a transversal intersection, right? I have this whole line segment intersection. So what we do here is what's called stable intersection. So we take this formula you also saw on Monday on the blackboard, right? We take our curve line lambda, we perturb it a little bit away so that we get transversal intersections, then we compute the multiplicity, then we take the limit of epsilon to 0, and that way we get the lifting multiples, the intersection multiples. So in our example, how does this look? I take my lambda plus epsilon, right? So this is the line. I perturb it, so it's a little bit perturbed. So I see now 2 intersection points here. And for these, I can compute the intersection multiples, right? So this is 1 in both cases because I get the just identity matrix for the direction of the system. 1, 0, and 0, 1. So the limit, when I take the limit, the sum it's 2. And these 2 points, so the intersection points, they mean to the 2 vertices of this line segment. And then the actual tangency point is by chip firing the middle of this line segment.
I have a question.
Yes.
Is it obvious that if we chose a different vector to displace this line by, we would get like the maybe different intersection multiplicities of the 2 other lines, that their sum is the same?
So I don't think it's obvious. I think it's part of the theorem for stable intersection. You see, in this case, at least, it's what you can see. Sorry, if I perturb the line in the different direction, I get still 2 intersection points, but the direction vectors are different. So in this case, it would still be 1 plus 1, but there might also be cases where I move maybe to 1 intersection of this. This is not obvious. It's part of the theorem. Okay. So what we see is that this red line here, we have 2 tangencies. So it's a bitangent. One more thing that we see here is that if I take this line and I move it up and down along this, is very hard to see. There is something yellow here that you can move the vertex of the line a little bit up and down. Right? So I don't change this intersection here at all. And this intersection here stays in the same edge of the tropical curve. So it still has the same tangency, same intersection multiplicity. So it stays a bitangent. So this Quartic curve, we've already seen there are infinitely many tropical bitangents to this curve. And we class these all together in a what we call a bitangent class. And this is how the decorations on the previous picture were to be read. Is this line segment tells me any vertex, any point on this line segment gives me a vertex of a tropical line that is a bitangent to this. Very important. So, yeah, let's go back to the picture and here, right now, such a line segment will tell you any vertex on here gives you a line that is bitangent. And then if it's just the vertex, this vertex is just the vertex. And therefore, we see here there are 7 such classes of bitangents compared to the 28 bitangents in the classes. What's the difference? What's the red coloring? The red coloring just tells you that the vertex is on the curve. So in this picture, it's obvious, but that is on the curve. But yeah, so it's red if it's on the curve, and the vertex is non-filled if it's at the same time a vertex of the curve. This is important for the classification of all these possible shapes. Thanks for the question. Any other questions?
So in this case, you have like 28 segments, right? So you show like 28.
There's 28 real bitangents here, like the red ones. And here
Yeah,
I have
for
7.
your curve, you have like 28 like segments, let's say, or lines, right? Or do you have a class for each?
I have 7 classes, 7
Just 7?
bitangent classes, just
Okay.
7.
This, okay.
Yes, there will. This is a theorem. There are always 7, and classically we have 28. And I will now tell you what's the connection. Well, after so this is the classical definition for a tropical bitangent line. It goes to a Baker and Morrison 3 we have either 2 intersection components with stable intersection multiplicity 2, like the example that I showed you, or we have 1 intersection component with stable intersection multiplicity 4. You will only this does happen, but the examples in this talk will all in the first case. So the promised connection between 28 and 7. So classically, right, Quartic curve over the complex numbers has 28 bitangents, which goes back to Flicker and 1824. And on the real side, we have 4, 8, 16, or 28 real bitangents. And this is work by Flicker and Zeuthen, 1839, 1820. Now, tropically, there's a theorem by Bakelin, Morrison, Flicker, and Wren that says we have always 7 bitangent classes. So, like in the picture that it's. And the connection between 7 and 28 is 4. Okay? And this is a paper by Yoel Glenn and Hannah Marvick, that each of these 7 bitangent classes each lifts to 4 complex bitangents. So we have every one of these bitangent classes, one class gives rise to 4 complex bitangents. So we cover our 28. So the story on the real side is the paper by Angie and Hannah. On the real side, they determined lifting conditions of the real numbers, and they see that for each of these conditions, if it's satisfied, the class lifts 4 times over the real numbers. If it's not satisfied, it doesn't lift at all. The 0 or 4 is very similar to the 0 or 8 that we've seen in Angie's talk for the tritangents. Okay, so 0 or 4 for each, so we're not quite yet there to recover the 4, 8, 16, or 28. And this was done by Martin Hansen in a computational tool where we computed all these for all these lifting conditions that Angie and Hannah had computed. We checked, right, for every Quartic curve, and we see, well, it's always 1, 2, or 4 classes that lift. So if they lift, they lift 4 times, so we recover the 4, 8, 16. Okay, so all said and done. Not quite. There is one word here in the title of the slide, and that's generic. So this is the short story of bitangents to generic quartics. And what's the new result I'm going to tell you about today is that there was one non-generic case here that we couldn't solve, and it's in my new preprint. Yeah, so I'm going to get to that later. Okay. So let's first go, before we can get to the very newest result, we need to kind of first acquaint ourselves with the results that were done before, so that we understand where is the gap, what's the problem, what can we do about it. So this slide shows you some of the results of the paper by Angie and Hannah Marvick. So here in this picture you see all these possible shapes for bitangent classes. So you've seen this as decorations on the Quartic curve before. This is like all the possible kind of decorations that you can have, from 0 over 1 to 2-dimensional families of tropical bitangents. And then by a duality, we can determine certain edges or triangles that you have to see in the dual subdivision. And that if you have this shape, then you will see these edges in the dual subdivision of the Quartic curve. And they determined these lifting conditions. These are conditions on you have the tropical Quartic, you fix an algebraic lift. Then you look at the signs of the coefficients of that algebraic Quartic. And the signs of these coefficients are the signs that appear here in the table. These signs need to satisfy that they're positive so that we're able to take square roots to compute the bitangents. We need to be able to take square roots, so this is why the signs are so important. Okay, so maybe let me just check. Skip this one. So what Martha and I did is we grouped together all those shapes that can deform into each other. So very briefly here on the slide, you see that I have the same combinatorial type of the Quartic, so I have the same dual subdivision, but different edge lengths give me different shapes. This decoration down here on the graph, it changes, right? Just because I change the edge lengths. Here the line would stop at this edge, and here I can go down. And Marta and I grouped these together into these, and now we have a one-on-one correspondence. So we see one of these shapes if and only if we see these edges here in the subdivision. Before it was just I see the shape implies I see the edge in the subdivision, and now we have a one-on-one. If I see this shape in the subdivision, I know one of these shapes can be there. And all these shapes in these groups together, they have the same lifting conditions. And this is what we, this is our theorem, and real lifting conditions for these tropical bitangent classes for a generic topically smooth plane quartic depend only on the zero subdivision. So you only need to know this unimodular triangulation, and then I can tell you all about the lifting conditions for the bitangent classes. I don't need to know the exact tropical curve. I only need to know the combinatorial. And well, this holds even if you want to lift the quartics over other non-Archimedean valued hence-yielding fields of residue characteristics not equal to 2. Because the only thing is that we need to be able to take these square roots to compute the real bitangents. So it's not really important that we have this real lifting condition. Just lifting itself only depends on this combinatorial. Okay, so now that we have that, it was a discrete counting problem. There are finally many of these unimodular triangulations. Up to S3 symmetry, there are 1,278. 8 of them are non-generic. I'll come to that later. And for all the generic ones, we computed these lifting conditions and we recovered them for 8, 628.
You mean by generic tropical curve?
I
What
will
is
tell
generic
you.
in algebraic and in tropical?
It's a different. It's very concrete, and I will show you.
Okay.
Okay. So this is the result here, and we did this by implementing an extension from software Automate and creating a lot of data that's on the database quality for this. Okay, so here's the answer to your question. What do I mean by generic? Generic is kind of important word. We have 4 things that a smooth topical quartic needs to satisfy to be generic. The first one is that if my curve contains a vertex adjacent to 3 bounded edges with certain directions. So this is going to look like this. So I have a vertex, I have bounded edges, so here's something going to happen. I have one edge in this direction, I have one edge into this direction and one into the diagonal direction. These are bounded. Something like this in my tropical. This is the first one. If we have this, then there has to be a unique shortest edge. And with the length, I mean the lattice length. Okay, so here we have like length 1, this is 1/2, and this is 1/2. So here we have a unique shortest edge. This is the first condition, and this is the And then the other conditions are that a lift of the curve, so this is more a condition on the lift of the curve, of the quartic curve. The lift has no hyperflex, there's no bitangents where the 2 tendency points coincide, or that the coefficients of the lift need to be generic enough that if we have tendencies on the same leg of the tropical curve, they can't lift at the same time. This is more a condition on the, these 2 are more conditions on the lift of the quartic curve. And the last one, that all the tropical bitangents are non-degenerate. Well, this is also something that we want to see. We want to see an actual bitangle, a tropical line with 3 legs and a vertex. We don't want the vertex to sit at infinity and we only see like one ray. This is kind of not a tropical line. Consider. So the one condition that is kind of the most heavy in here is the first one. This one is an actual condition on my quartic curve, and it can be, well, it can happen that this is not satisfied, right? So here we see then this is the shape that we have to take care of, and for these non-generic quartics, we can't lift a bitangent class of shape C. And this is the bitangent class that appears if we have the vertex at exactly this vertex here. So if my bitangent, my line, my tropical line, I need a different name for this. Is exactly sits at that one vertex, and we have these 3 bounded edges coming together. And then if these bounded parts here are the same length, then the theory that was used to determine the tangency points, determine the lifting conditions, which is called, this technique is called tropical modification. We don't know how it works. We know how it works if we have a unique shortest edge, otherwise we don't. So in these non-generic cases, we can't lift this by tangent plus C. Right? So we see with some curves, it's not such a big deal. Like this curve here, well, it's all these edges have the same length, so I can't lift it, but I can change the edge length so that I have a unique shortest edge, and it's still the same combinatorial type, and these have the same subdivision. So in this case, we can think of it like, okay, I have my one bad case where the edges have the same length, but I can change the edge length a little bit. Then I get my unique shortest edge. I can compute. Compute the lifting. I can get to this. On the other side, I can change different edge lengths. So it's kind of like a hyperplane section, right, of our secondary cone. That's not so nice. And as long as it's like lower dimensional, we can say, well, this is not such a big problem. Okay. And this is a proposition of my PhD thesis. There's a non-genericity locus for the secondary cone. For generic unimodular triangulation, is only like it's the intersection with at most 3 half hyperplanes. So this non-genericity locus is really just half hyperplanes. For generic triangulations, what those are, I'll tell you in a second. So in these cases, it's not a problem. We can compute the lifting conditions of shape C by, well, this thing, we know how it looks in the other parts of the secondary cone, and by continuity arguments, we can prove that it's the same also on these non-genericity locus. However, now it's a new genericity assumption here on the triangulation list. And this is because things like this can happen. I can have this shape here in my triangulation, and then the quartic curve cannot have a unique shortest edge in this triplan. So it's very small here. I'm sorry, but the curve otherwise would have gone too big. So this is here, that's the vertex that we're looking at, and there are 3 edges, 2 small ones coming out and 1 long. And these 2 small ones always have to have the same length. So it's not possible that one of them is shorter than the other, and this one is always going to be longer, because the combinatorics of the subdivision is telling me it's not possible. And there are 8 of these, up to S3 symmetry, there are 8 such unimodular triangulations. So there are, up to S3 symmetry, 8 secondary cones in the secondary fan that we cannot determine the lifting conditions of this of shape C. That's the problem. So what do we do here? So we can't use continuity arguments or anything. We need to do something else. And the idea was to use the correspondence between real topology and the number of bitangents. So maybe, so we know if we have certain number of ovals, this is work by Zeuthen from also the 19th century. Now, if we have like 0 ovals with 0 real bitangents, for 1 oval with 4 bitangents. If the two ovals are nested, then we see 4 bitangents. 2 non-nested ovals, 8, 3, 16, 4. 20. However, there is a little problem. Right, so I know I can lift all the other 6 bitangent classes. So I get some multiple of 4 that might or might not coincide with those numbers. And I can do this computationally, but computationally, I was not able to distinguish between 2 nested or 2 non-nested ovals. So I can show you what I mean. So let me show you this. Computation, this was what was already implemented in Polymer, and I will just have this on a slide further to show you. Okay. So the problem is, I could see like if I have 24 lifts already, right? I know all the other 6 bitangent classes lift. I get 24 real bitangents. I know the last one will have to lift, right? Because like 24 is not a valid number. But if I have 4 lifts, then I don't know, is 4 complete, or should I actually see 8? And I need to be able to distinguish between these 2 cases. Problem clear? So let me introduce you to the real tropical curve. For us, it will be a couple of a smooth tropical curve together with a sine pattern. And this sine pattern is on the lattice points In our case, it's the picture. What you think of this, as I said before, right? When we fix a lift of our tropical quartic, the signs of the coefficients of the algebraic quartic are what matters. And in these signs are what we look at. These sign pattern on the lattice points, and the sign patterns together with the unimodular triangulation of the quartic curve is what we call the combinatorial type. Now, what we are going to need is real tropical geometry, and here the idea comes from logarithmic limit sets and approximations via amoeba. So here the idea is that if you have an algebraic curve, you look at this map log t that takes your points x, y, and maps them to log base t of the absolute value of x and absolute value of y. The image of this is called the amoeba of the curve C to the base t. And theorem by Kaplanov tells us that if we allow that t go to 0, the limit of this is going to be the tropical curve. Top C. And this pictures out of the paper by Shaw illustrates this. So in black you have the amoeba, and in red you see the top. Now, our idea, or the idea that I want to give you, because I don't want to get too deep into the theory, is that when we take here the absolute value of x and y, right, because we need this to apply the logarithm, but that means we kind of forget, if instead of c here we look at r, we kind of forget which quadrant our points come from, right? Because we're taking the absolute value. So we want to introduce three more quadrants that remember where the points come from. Okay, so add if one triangle here, which represent our tropical plane, then we're adding 3 more copies, and each copy remembers kind of where the signs of my x and y were coming from. Okay? And then we identify like this, like the arrows show on the picture, and you see this real tropical plane is, if you've seen, you should maybe have seen this picture before in topology class. This is your real projective plane. But for us, this is the real tropical. And now the patchworking technique developed by Vivo, it's not on the slide, but it should be, tells you the following. So if you have your combinatorial type or your quartic curve with a sign pattern, what you do is you take 3 more copies of it, like this, and you adjust the signs in the following way. Whenever you have an odd distance to the spine, which should make this black, okay? Then you swap the sign. This corresponds to, well, if you have your monomial with an odd exponent and you plug in a different sign, then the sign will come out, right? -1 to the power of 3 is -1. So I need to swap the sign. So the minus up here would become a plus. If I have an even distance, then I keep the sign. Make sense? If I have x squared, it doesn't matter if I plug in 1 or -1. So now we have this bigger triangulation with a lot more signs, right? And then what we do is we separate the positive and the negative signs. This picture here, what we do with green, right? I cross every edge that goes between a positive and a negative sign. And what results? The result is this. This is the real part of the tropical curve. Okay, this is what we call the real part of the tropical curve. This is the technique how you get this. This clear so far? Now, the big theorem by Vivo is that this notion of real part of the tropical curve actually makes sense if you go back to the connection with the algebraic world. Okay, so it's a long theorem here. Basically, what the important part is this down here, right? So there exists a homeomorphism from a real algebraic curve that maps the real points of an algebraic curve onto the real part of the tropical. So that also does. we have a lift. It's possible to find a lift of the tropical curve that has exactly this real structure. So this is what we want to use in order to see the real part of our tropical curves and to determine the real topology to see about the number of Bitangents. Okay? So this is here. I hope it's big enough. This is like a screenshot from out of Ptolemaic. Okay, so I have my Quartic curve and my sine vectors, and then I can ask Ptolemaic to do the patchworking. This is what this is called the patchworking, right? I can ask Ptolemaic to do the patchworking and tell me the Betty numbers. Betty numbers are 2, and so I only need the first of these 2 numbers, and this will tell me the number of ovals that I see. Okay, like real topology. And it only tells me the number of ovals. It does not tell me if, like here it's 2. It does not tell me if these 2 are ovals are nested or not nested. What I can do, however, is I can ask Ptolemaic to visualize this real part of the curve. So I will get this picture, yeah, and then I need to, and I like glue the edges as I had in this previous picture, and so these 2 correspond to these below, and I will see I have 2 non-nested ovals. I have one over here, and the other over here. But as I told you, like, so I have 1,278 triangulations, and I have 2 to the power of 14 possible sign distributions. I don't want to draw a picture for all of them. Even if I don't have to draw it myself, I don't want to look at them all. So even if I say, okay, for 1,270, it's generic, I don't need to worry, I can just take these 8. It's still 2 to the power of 14. I don't want to do this by hand. So I need to come up with something smart. So I looked a bit more at this approximation by amoeba. And this can happen in 2 ways, right? So this picture we've seen before, but this also is out of this brief introduction to tropical geometry, so out of the same paper. What you see here is that the amoeba does not approximate an edge like this, but like this. Like the amoeba crosses over the edge. And this is what we call twisted edges. And these twisted edges will be able to help us to determine the being nested or not nested of the ovals. Okay, so this is the combinatorial definition of what is a twisted edge. So basically it means in the metric graph of our tropical curve, if I have a cycle, the primitive integer vectors of the twisted edges have to sum to 0 modulo 2. And then if I have a real, so that's then the twist miscible, which means it can come from such an approximation. And Regali, Ekenberg, Mikakin, and Shaw showed actual conditions for a bounded edge to be twisted if we have such a real tropical curve, so a tropical curve with the sine pattern. And they say, okay, I see a bounded edge V1 to V2 in my subdivision, and well, it's a bounded edge, so it's dual to a bounded edge of the curve, so it is adjacent to 2 triangles in the triangulation. And then I can look at the vertices of these 2 triangles that are not my edge, so A1 and A2. And if these 2 are equal modulo 2, and the according signs have a product that's equal to -1, then the edge is twisted. And if they're not, the coordinates are not the same modulo 2, then I need to look at all the products of all these 4 vertices, and if it's 1, then the edge is twisted. So these are conditions, again, sign conditions on the edge, on the real tropical curve to determine which edges are twisted. And this is something that, well, we can easily implement software to do these checks for us, to tell which edges are twisted.
So wait, I have a question. So
Yes.
what are these A1 and A2?
So these are the lattice points of the triangles in the subdivision that contain this edge we want to.
In that example, let's say A1 would be 0, 0, and A2 would be. I see.
Yeah.
Okay.
So this is just one example, like these A1 and A2 could sit anywhere.
Yeah.
It's just the easiest way to draw numbers.
So it's a lattice point.
Yes. And there is a theorem patchworking theorem by Wheel that says like for any twisted miscible set for a non-singular tropical curve, there exists again a family of non-singular real algebraic curves that the tropical or that converges to this tropical curve that keeps these twisted edges. So that just tells us basically just tells us it makes sense, right? It fits together. We have these definition of the amoeba with the twisted edges. We have the combinatorial description of the twisted edges, and they make sense together. If you approximate the twisted edges that we defined by the sign patterns, will exactly be the twisted edges. So far, you might still ask yourself, why am I talking about twisted edges? I still haven't told you how we can use this to determine whether two ovals are nested or not. And this is where it's important to know about dividing curves. So a complex curve is called dividing. We have the real locus. So if we take the real locus of the curve away, it becomes disconnected. The real part divides the curve, the complex curve. So this one is called dividing. And we tropically, when we say, okay, tropically the curve is dividing if it's the tropical limit of family of dividing curves. So we just we'll kind of pull it back. Yeah? And then the theorem by Haas tells us how to, for a tropical curve, how to determine if it's dividing. Combinatorial. And it's dividing if and only if we have for every cycle in our tropical curve, the number of twisted edges is, and again, this combinatorial condition is something that's very simple to check for a computer. Just tell a computer the twisted edges, go over every cycle and tell me, do you see an even number of twisted edges? This is again something that's easy to implement. And here is finally the connection. Why twisted edges? Why dividing, right? So if I have a tropical quartic curve with two ovals, then these two ovals are nested if and only if my curve is divided. And that's kind of like last week. Remember, the twisted edges, we needed them to be able to determine whether the tropical curve is divided. So now I know about two real ovals are nested, then we have to know 4 real bitangents. If they're not nested, we have 8 bitangents. We know this dividing, we can determine the twisted edges. That was all combinatorial things that we can implement. So we now have a computational method to determine lifting conditions for shape C, because I can tell you exactly how many ovals the real tropical curve will have, which means I know how many real bitangents I should be able to see. I know how many I can see, and that tells me what's the difference, and this tells me does shape C lift or not. And yeah, this is the algorithm. Right? I determine all the other. For any non-generic unimodular triangulation, I go over all these 2 to the power of 14 sign vectors. I compute the number of real bitangents that I can compute, and then I compute the Betti number. And if the Betti number is 2, I need to check whether the curve is dividing by using these twisted edges. And well, then I know I compare the two numbers of real bitangents that I have computed and the number that I should be able to see, and I can collect all these sign vectors for which the class will lift. And what do I do now? Now I can, well, this is great, but now do I every time have to check my sign vector against like this big document that Alheydis produced with all the possible sign vectors for shape C to lift? No, you don't have to do this. I took all these sign vectors and I checked it against the formula that Angie and Hannah computed for the generic case. And it turns out this formula was true exactly if and only if the sign vector was in my list. So the sign conditions for bitangent classes of shape C are the same whenever, so for generic or non-generic unimodular triangulations. We still don't know how the original technique of tropical modifications works that Angie and Hannah used for the non-generic case. For the generic case, we don't know how it works in the non-generic case, but we know it should give the same results. One more thing that I was able to determine here is that, the result by Angie and Hannah told us that these tropical bitangents, whenever they lift to real bitangents, they are totally real. That means that the bitangent point, these two tangency points are also defined with the real numbers. And this comes just from the computation that they did with this tropical modification, actually computing the exact formulas that tells you that also the tangency points are real. So for this non-generic case, we don't know because we don't know how the tropical modification works. But what I can say is that at most one real bitangent is going to be not totally real, and that goes down to Klein's inflection formula for inflection points that tells you that the number of inflection points plus the number of real bitangents, totally real bitangent is d times 2. So he is 4 here, so this is 8. And this is 6 in this case. So that means there can be at most one totally real bitangent. So this is a history. Yes. Okay, so what I then did, I had all this data because I computed all these, all this data for these all these triangulations and real tropical bitangents. So what one can see is one can ask, okay, for any unimodular triangulation, is it possible to find a sign vector such that I get a maximal algebraic curve, so that I get 4 ovals and 28 bitangents? And this is what this table tells you. This table tells you that 1,207 unimodular triangulations for which you can find a sign vector that gives you either 4, a sign vector for 8 bitangents, a sign vector for 16 bitangents, a sign vector for 28 bitangents. There are only 2 triangulations for which you can only find sign vectors to be to 16 or 28 bitangents. But each of the triangulations, we are able to find a sign vector or sign distribution to give us 28 bitangents, so 4 ovals for the real. And that's this table basically is this the theorem when frequent, where so we have all these ovals and real bitangents. Topically, we see like 1, 2 nested, 2, 3, 4, and the corresponding number of real bitangents. And then these big numbers below tell you how many combinatorial types of real tropical quartics achieve this real topology. So maybe forget the first line, just look at the second one for the moment, because this is up to S3 symmetry. So the total number, if you count together all these like big numbers here, you should get 1,278 times 2 to the power 14. Okay. And out of these, you see like 1 million something have combinatorial type, 4 ovals and 28 real bitangents. And this line up here, that's for if you don't take into account the S3 action, so then you get 7,422 unimodular triangulations times 2 to the power 14. And check. So I did all the computations modulo S3, but you can always check the orbit size, and then you get these bigger numbers. Questions so far? No? Okay, then I have a few more minutes to show you this Ptolemaic extension that I implemented originally together with Marta, and I added on some new functionalities now that we have these real tropics. So this is Jupyter notebook, that runs a Ptolemaic kernel, and I compiled it before so that that's hopefully everything is still correct, so that I don't have to compile it now live, because usually then things go wrong. So here in this line, I connect to this database PolyDB, which contains all the data that I computed during this project. So if you want to look at your favorite unimodular triangulation and learn about its real topology of the tropical curve, you can go to the database and have a look at it. So I get the collection. It's called tropical quartic curves, and I find one curve. But I take the one with ID number 511, and I ask whether this is a generic triangulation. Okay, so whether it's containing this certain pattern of triangles, right, that makes it difficult for a line segment to be uniquely short, and it's not generic. Right, so it's exactly one of the cases that we were not able to completely understand before. And now here I'm asking for what's called deformation motives. These are just the names of these shapes that Angelica and Hannah computed for these different bitangent classes. And for each of these, we have these sign conditions. So here, this asks for the sign conditions. So this tells you, okay, so we have a labeling of these lattice points. So I have the unimodular triangulation is of 4 delta 2. So I have these numbers of lattice points, and we label them fixed. So it's always 1, 2, 3, 4, 5, and so on until 14. Okay? And so this is 10. So I'm going to pick this one to explain this. Okay, so this one tells you that the coefficient belonging to the constant term and the term for x to the power of 4, these need to have, the product of these needs to be positive. This is what this 0, 10 here in the condition tells you. If this is satisfied, then this bitangent class, which one did I pick? I picked the fourth one, so G would lift over the reals. And if there is a -1 at the top, it just tells you that the product of these signs needs to be negative in order so that we that the curve can sign conditions on here. These ones for shape C are the ones that are new now. So shape C was the third one, so this is the new sign conditions that for an older version of this extension and the database you would not have been able to see. This is the new condition. And then I can ask for the oval information on the ovals, on these real ovals. And this is basically this data that you see here for all these 1,278 is going to fuel this big table at the end that I showed you, these like big, really big numbers. Right? So it tells you that for this specific triangulation, which maybe I should show you a picture of this triangulation. One. Visualization didn't work in this in the Jupyter notebook, but that's a triangulation, 511. This is the triangulation. Right, so it tells you there are 4,096 possible signs that you can apply to this triangulation to get one non-nested oval. And this is an example sign distribution. And you see there is no possible way to apply sign distribution to get two nested ovals. This doesn't, you will always see non-nested ovals if you have a tropical quartic with this triangulation. And yeah, then I can also, here I pick my real quartic curve with a given sign distribution, and I can ask for the number of real bitangents. So this sign distribution is the one that I picked here from this as an example sign for two non-nested ovals. So I see two tropical bitangent classes that will lift, which tells me like classically I get 8 real bitangents. I can ask for the exact shapes. I can ask for the twisted edges in the dual subdivision. I can ask if the curve is dividing. It's not, since the two ovals are not nested, right? And I can even, I can also visualize the, yes, so I can visualize this. I can visualize the real part of the tropical curve. There is one tiny oval here and a really big one for the rest. So there are two non-nested ovals. I hope you can see. You can of course also just visualize the tropical curve. And I think I'm not going to go into the second example because we've seen most of it already. In the first one, I'm going to say thank you for your attention.